All right, so now I want to give you a couple of more examples because time is, and these kinds of parameters and variables are not the only ones that are important for calculus. If it were only this kind of physics that was involved, then this would be a much more specialized subject than it is. And so I want to give you a couple of examples that don't involve time as a variable. So the third example I'll give here is the letter T often denotes temperature. And then dt dx would be what is known as the temperature gradient, which we really care about a lot when we're predicting the weather, because it's that temperature difference that causes airflows and it causes things to change. And then there's another theme which is throughout the sciences and engineering, which I'm going to talk about under the heading of sensitivity of measurements. So let me explain this. I don't want to belabor it because I just am doing this in order to introduce you to the ideas on your problem set, which are the first case of this. So on problem set 1, you have an example which is based on a simplified model of GPS, sort of the flat Earth model. And in that situation, well, if the Earth is flat, it's just a horizontal line like this. And then you have a satellite, which is over here, preferably above the Earth. And the satellite knows exactly, or the system knows exactly where the point directly below the satellite is. So this point is treated as known. And I'm sitting here, okay, with my little GPS device. And I want to know where I am. And the way I locate where I am is I communicate with this satellite by radio signals. And I can measure this distance here, which is called h. And then the system will compute this horizontal distance, which is L. So in other words, what's measured, so h measured by radio waves and a clock, or various clocks. And then L is deduced from h. And what's critical in all of these systems is that you don't know h exactly. There's an error in h, which will denote delta h. There's some degree of uncertainty. The main uncertainty in GPS is from the ionosphere, but there are lots of corrections that are made of all kinds. And also, if you're inside a building, it's a problem to measure it. But it's an extremely important issue, as I'll explain in a second. So the idea is we then get to the get at delta L is estimated by considering this ratio, delta L over delta H, which is going to be approximately the same as the derivative of L with respect to H. So this is the thing that's easy because, of course, it's calculus, right? Calculus is the easy part, and that allows us to deduce something about the real world that's close by over here. So the reason why you should care about this quite a bit is that it's used all the time to land airplanes. And so you really do care that they actually know to within a few feet or even closer where your plane is and how high up it is and so forth. All right. So that's it for the general introduction to what a derivative is. I'm sure you'll be getting used to this in a lot of different contexts throughout the course.